So now I will explain the first graph traversing algorithm, that is breadth-first search. In breadth-first search, queue data structure is used. In breadth-first search, all the nodes at a particular level are explored before jumping to the next level. Generally, the space complexity of the breadth-first search is equal to the number of nodes in the graph. This breadth-first search is generally used to find connected components of the graph. It is also used to find the presence of loop in the graph. It is used to detect articulation point in the graph. So articulation point is such a node whose removal disconnects the graph into two connected components. That node we call it as an articulation point. If articulation point exists in the graph, then we say that the graph is not biconnected. This is very important terminology. What is biconnected graph? So, for example, in this graph, if you are observing that node D is an articulation point, because when we are removing this D, removing of a node means we have to delete this node along with the edges falling on this node. If removal of D disconnects the graph into two connected components, then that node we call it as an articulation point. Like in case of this graph, if we remove the D, we also are going to remove these edges, three edges. Removal of D results in two connected components. One connected component is F, E, G, and second connected component is A, B, C. That's why D is called articulation point. Similarly, even if we are removing E, then also removal of E disconnects the graph into two connected components. Therefore, E is also called as the articulation point. One graph can have more than one articulation point. Similarly, in this graph also B is an articulation point. As the articulation point exists in this graph, both the graphs are non-biconnected graph. In some books, you are also required to find the presence of bridge. As the articulation points refer to the node, bridge refers to the edge. The removal of edge, if the removal of edge disconnects the graph into two connected components, then that edge we call it as the bridge. Obviously, one end of the bridge is definitely going to have an articulation point. So these are some of the applications. The real life application of the detection of articulation point is you can detect a failure of node in the network. This is one application of detecting articulation point. Now I will explain you how this breadth-first search algorithm works with the help of this graph. This we have taken in the first quiz. So as you are aware about the adjacency representation of this graph. So if we are going to represent this graph in terms of adjacency matrix, it is a directed graph. So you will get adjacency matrix of size 10 by 10, where the rows are labeled as the nodes A to J, as well as column we are going to label as A to J. The entries in this adjacency matrix is either 1 or 0. If edge exists between any pair of vertices, then that entry is 1. So suppose edge exists from A to C, then the entry in the first row of A for column C is 1. Similarly for B, A is adjacent to B, but B is not adjacent to A. So entry of B for the column B, entry in the row of B and column A is 1. Similarly, this adjacency matrix will be filled. Now we look for the breadth-first search sequence of this graph. We can find out this BFS sequence from any one of the source. So assume we'll consider G as a source. So Q is used for the breadth-first search. We have also seen this in case of trees. Breadth-first search is also known as the level-wise traversing of the nodes. So breadth-first search sequence is actually giving you the sequence of node in which the nodes are visited. So assume at G is our source node. Initially all the vertices are not visited. Their status is not visited except for the source. So insert source in the queue. Then you delete the source and print that source. Then you have to insert all the adjacent nodes of G those adjacent nodes you can capture from the adjacency matrix for the row G. For row G, whichever entries are 1, those are the adjacent elements of G. So adjacent nodes of G are A and J. So we'll insert them in queue and mark them as visited. You again check if queue is not empty. We are going to repeat the process of removing a node, inserting its adjacent node and marking their status as visited. So remove A, print it, insert all the adjacent nodes of A and mark them as visited. So adjacent nodes of A is C. So mark it as visited and insert. Again, queue is not empty, so delete J, print it, insert adjacent nodes of J and mark them as visited. Again, queue not empty, delete the element, print it, insert all the adjacent elements of C and mark them as visited. Similarly, H is deleted, printed, adjacent nodes of H is C, which is already visited. So we'll proceed for the next node, that is B. Delete B, print B, insert all its adjacent node, that is F and E, mark them as visited. Again, insert F, as there are no adjacent nodes of F which are not visited. So repeat the process until queue is empty. And therefore you will get this sequence as G, A, J, C, H, B, F, E. If you are observing in this sequence of BFS, D node is not there as there is no incoming edge towards D. So D should not be there. So this was the execution of the BFS algorithm.